Welcome. Today's lesson is entitled Infinite Geometric Series. And so just wanted to recap what we've been doing so far. We've looked at sequences in general, and then we focused on two particular types of patterns. We looked at arithmetic sequences and arithmetic series. So one is just a pattern of numbers, the other is the sum of that pattern of numbers. Then we looked at geometric sequences and geometric series, what we would consider finite, just a certain number of terms. And now, everyone, we get to this stage right here where we're going to add an infinite number of terms together that are geometric in nature. And being a series, again, we're going to take the sum. So infinite geometric series. So let's go ahead. I've got a couple investigations to get us thinking about how this will play out. And so what we're going to do, because we're at this stage can't really talk about adding an infinite number of values together, we're going to take what is called the partial sum of an infinite geometric series. So notice how this is written here. First and foremost, I have a few terms added together. And with that dot, dot, dot at the end, basically this pattern goes to infinity. And if we're going to really talk about this in its relation to the title of the notes, we should be clear about one thing. Is this geometric in nature? So first and foremost, I would kind of look and any term divided by the previous term. So this divided by this divided by this, etc., right down the line there. From my vantage point, I'm getting an R value of 1/2, and I'm just going to write that in there just like that. So a couple things to note. Number one, I just saw that it is geometric. Number two is because we're adding the numbers together, it is a series. And number three, because this is going to go on indefinitely, we're going to consider it infinite. So it definitely fits that idea. And what we're going to do is explore sort of the partial sums of this infinite geometric series. And so here's what I'm going to ask you all to do just over to the side. Let's go ahead and just do an n right here and an s sub n right here. And just because I have a good sense of how this will play out, everyone, if you would, put a little 0 right here for me. And let's just do a 1, 2, 3. And how many are we going up to partial sums? It looks like 6. So all the way up to s sub 6. And then as a result here, let's go ahead and do, I'm going to do a 1, 2, 3, 4, 5, 6. And I'm going to just go up to 8 there, not that it really matters a whole lot by any means. Okay, now what I'd like to do is fill in these values and then kind of plot these values and take a look, see what the graphical pattern tells us. So first order of business, guys, is to talk about the partial sums. So this means add the first term together. Well, obviously it's just 3. Everyone put a little 3 right in there for me. S sub 2 means add the first two terms together. So 3 and 1.5 should give me 4.5. All right, so that is S sub 2. Next one, let's add it to the list here. Let's just keep a running total. Add this to what we have. I think I can pull off a couple of these. Looks like we're at about 5.25. Okay, very nice. Let's see, now let's add this on top of that. So this would be the first 4 terms added together. Okay, I think I can do this. You may have to confirm that for me, although I'm going to play it out. I think I get 5.625. Okay, that sounds good. I'm probably good for one more before relying on the calculator here. I can probably add that in. If I add that term on top, I'm going to go with that. I should probably confirm that piece, but I'm going to go with that right there. And then this next one, adding this on top of that, that one I'm not going to be able to pull off. So I'm going to go ahead and grab my calculator. First of all, I should probably confirm that other one. So let's see, 5.625. And I'm going to add that last entry that I dealt with there. That was the 5th one. Okay, and it looks like I was right there. That's good. And then, everybody, what I'm going to do is add the 6th term on top of that, and this will be our last partial sum. So I'm hoping everyone is okay with just what I'm doing, 5.90625. 5.90625. All right, sounds good. Now you can get a sense for the type of number that would come next, and next, and next, and next. And as I said, this really just goes to infinity. And if I kept going here, adding the next one and the next one and the next one on top of that, what would be happening to our sums? Well, let's see if we can again sort of look at this visually here and then see if we can develop something conceptually. So it looks like the sum of the first term was just 3. So everyone, let's create a little scatter plot out of this. And then second jumped up to about 4.5. Third, about 5.25 there. Just do the best you can on that. Fourth one, 5.625. Okay, fifth one, about 5.8 and change. Sixth one, 5.9 and change, somewhere up there. And what I'd ask you to do is think about the numbers that I would continually add and what would be going on with the sums here. So it's interesting. We're trying to format something here where we're adding an infinite amount of values together and somehow getting a singular answer. You would think that just adding an infinite number of values together would be meaningless because it just goes to infinity. But because it fits this infinite geometric series, you kind of see something intriguing about this. And if I kept adding numbers, keep going and going and going forever and ever and ever, the question on your paper, I guess, kind of speaks for itself. It says, will the graph ever reach 6? And I guess I would ask you that. As we keep adding the values that would make this pattern true and keep adding one on top of the other on top of the other, will it ever actually hit or cross the number 6? No. And that's what you're going to write here. And so what we're going to write in is sort of our way around this. How do we add an infinite amount of values together and get some type of numerical answer? This is our way to pull that off. So here's what we would say. 6 is what is called the limit of the sum as n gets larger and larger and larger as n approaches infinity. And so it is as the limit, it is considered the sum of the infinite geometric series. So a finite sum for an infinite amount of values added together. And that's mathematically how it plays out. It is the limit of that sum as n gets larger and larger and larger. These values, these partial sums, would get infinitely close to positive 6 as n gets significantly larger. And so as a result, this is our numerical limit. N is considered our finite sum. Okay, good. We're going to actually come up with a nice looking formula for this piece as we go through. So keep that answer just in the back of your mind. But I'm hoping that makes sense. It's kind of working our way around a situation where, as I said, we're adding an infinite amount of numbers together and somehow getting a numerical answer out of that. Well, let's see the investigation 2. So it says use the partial sum of this infinite geometric series. Same thing here, everybody. Let's first of all confirm that this is geometric. This divided by this is 2. This divided by this is 2. And it looks like in each case, the R value is 2. Keep that in the back of your mind, if you would, by the way. And let's go ahead and do the same thing. Everyone, if you would, put a little n right there and an S of n up there. Now let's do, just going to throw a 0 right in there. 1, 2, 3, 4, 5, and 6 should be fine. I am looking at these numbers here. I'm going to go by 5s if that's all right. Okay, again, this does not have to be perfect, as we will see, but something like that should suffice. Okay, so let's see. I'm going to start adding them up there, and then let's look at this graphically. So the partial sum, first one, just 0.5. All right, now S sub 2. Add the first 2, everybody, and we get 1.5. Add the first 3, and I get 3.5. Add the first 4, and I get 7.5. Add the first 5, and I get 15.5. Add the first 6, and I get 31.5. Now think about this. Try to extrapolate, if you would. What would be the next term, and the next term, and the next term, and the next term? So what would be sort of the partial sums as I go 7, 8, 9, theoretically, all the way to infinity as those numbers get infinitely large? Well, let's go ahead and see. I mean, you might be able to sort of come up with a conclusion without me doing this graphically, but I'm going to do it anyway. So it looks like I had a 1 right there. I had a 1.5 right there. 3.5 right there. And then we've got a little jump. 7.5 right there. 15 and change right there. And on my last one, it jumps up all the way to 31.5. Looks good. Now, by the way, again, as I said, extrapolate a little bit. What would happen on the 7th and the 8th and the 9th if this pattern continued? Well, the next one would be up here, the next one would be up there, and it would be going off my board very, very quickly. So, as you can see, it is quite a bit different than the first investigation. Number one, it says, is there a limit to the sum as n gets infinitely large? In this case, there is no limit. The sum is going to infinity. So I'm going to write that just right up here. It looks like the sum is just going to keep getting larger and larger and larger. So as a result, if there's no limit to the sum, would we consider this one to have a finite sum in this infinite geometric series? And the answer is definitely no. So it does not approach a finite number like the last one did. So at this stage, what we're now determining is some infinite geometric series have a limit. They go to a particular number. Others do not. And so that's what we're looking at. All right, very good. And on your paper, it should say something like, when does an infinite geometric series have a finite sum? I'm going to have to write that answer just down here somewhere. But what's the major difference between the two investigations? And if you can see, it's all based on R. In the first one, the R value is 1/2, and in the second one, the R value is 2. And so we did not include negatives, by the way, here, and we'll get into that piece in just a minute. But essentially, here's going to be the key for us to be able to get a finite sum in an infinite geometric series. That R value has to be in between -1 and +1, if you can kind of jot that piece in there on your paper. So again, we didn't look at it in terms of a negative value. We just did a couple investigations with it positive. But if R is in between -1 and 1, it's going to have a finite sum. If it is less than -1 or greater than 1, like we saw right here, then you see it very simply does not have a finite sum. Now, just one thing to note, students have asked about this one over the years, and you don't have to do this on your paper, but when we have like an R value that kind of fits in on the lower end, maybe an R value of -1/2 or something like that, what's kind of fascinating about the way the sums work out is it would kind of go like this visually. I'd get a sum up there and a sum down there, a sum up there, a sum down there, up, down, and what would happen is you would be getting infinitely close from both directions towards a particular number. And so little above, little below, little above, little below. And in each case, as n gets larger and larger and larger, it would be getting closer and closer to that particular value. And so it would have a finite sum. It just doesn't act in the same way as this. It doesn't approach the number from just one direction. Yeah, kind of fascinating. All right, so there's a formula that works for this, and I think I'm going to have to work a little bit off to the side here. So let's do this. Actually, I'll do it above for right now, and then we'll kind of write this in. So here's what I'm going to ask you to do. Just on your paper, somewhere find a spot, and let's go ahead and do the finite geometric series. So that was this one. Just want to show you where our new formula is going to come from. And so that would be adding the first 10 terms together, the first 100 terms together, the first million terms together. And the idea is simple in that what would happen as n gets larger and larger and larger? So as n approaches infinity, well, with only particular r values, and so this is where we're going to be careful. So say, for example, my r value is like 1/2. That's within our interval for r, right? So if it fits the mold that we're looking at, and say I have an r value of 1/2, what happens when I take that number and raise it to larger and larger and larger numbers? So think about this for a sec. Numerically, when you do 1/2 to the millionth, 1/2 to the billionth, 1/2 to the trillionth, what happens to the value of that power here? Well, when I take that fraction and raise it to infinitely large numbers, extremely large numbers, this value, the power, goes to 0. Is everyone okay with that piece? This would get closer and closer and closer to 0. And then you end up getting 1 minus values that are getting infinitely close to 0. So this whole top, everybody, as a result, ends up going to 1. As n gets infinitely large, this part of our formula goes to 1. And then as a result, if this is going to 1, a sub 1 times 1 is just a sub 1. And so, long story short here, you end up getting this. A sub 1 times 1 is that, and the 1 minus r stays. And that's the formula. So it's weird, is conceptually, it is the hardest to wrap our minds around, but in terms of the 5 formulas, I guess, that we've seen up until this point, it's the easiest out of the 5 to use. Just very simple. A sub 1 over 1 minus r. Okay, good. So let me erase this piece, and I would encourage you to do the same, just so it doesn't get in our way. But I did want you to see where it comes from. It obviously uses the formula for a finite geometric series and watches what happens as n gets infinitely large. And the sum would get infinitely, well, the sum would get closer and closer to this. So it looks like there's an example 1 on your paper here. It says use the new formula to get the sum from investigation 1. So everyone, this would be kind of the situation at hand. We would be doing from the first term to the infinite term of, and if you remember correctly, that we started at 3. The r value was 1/2. So this would be our representation for the terms in that particular pattern. 3 times 1/2 to the variable minus 1. And very simply what this is basically saying is we should take the first term and divide it by 1 minus r, so 1 minus 1/2. And you could see everybody here, 3 over 1 minus 1/2. Well, this would be 1/2, and 3 divided by 1/2 is 6. And look how simple that is. So you could see, obviously, we looked at it from a very conceptual standpoint, and we speculated, quite frankly, on what would happen with the sum. And now, numerically, that bears out up here. 3 over 1/2 is 6. Okay. How about this, everyone? Just it'd be great for you to pause the video for just a moment and take about 30 seconds there, and just tell me. In each case, these would be infinite geometric series. A couple things that tell me that. First and foremost, the infinite part, going from 1 to infinity. The series part is the sigma, adding all the numbers. And the geometric part is the fact that this is exactly how we represent a geometric pattern of numbers. That is our formula for the kth term in a geometric pattern. So one more time, infinite, geometric, series. And not every infinite geometric series has a finite sum. All I want to know is a yes or a no. Okay, well, let's see. In this case, it's all based on r. There's your r. R has to be in between -1 and 1. This is less than -1, so that's definitely a no. This r value is right in there. It is in between -1 and 1, and so the answer is yes. And it's that simple, all based on r. Okay, in each case, it was infinite geometric series, but it's on r. All right, let's go for it. Next piece, everybody. So let's sort of do this. It says example 3, list the first 4 terms and then find the sum. So I figured we would sort of look at this from a partial sum standpoint. It is infinite in nature, so 1 to infinity, geometric, and it is a series. And I guess in this particular case, the first term I'm hoping you all agree would be 12. And then it looks like each term after that is a quarter of the previous term. So r is going to be 1/4. And so what that means is it looks like a quarter of 12 would be 3. A quarter of 3 would be 3/4. And a quarter of 3/4 would be 3/16. You know, et cetera, et cetera, et cetera, kind of like that. And if you just look numerically, 12 plus 3 is 15, plus 3/4 is, 15 3/4, plus this makes it a little larger. So I'm fairly close to 16 already just in the first 4 terms. Well, I don't know. Let's see how this does play out. Again, this is just for me to get a numerical basis, but really when I ask you to find the sum, it's going to be this simple. It's basically going to be this piece. I'm going to go ahead and write it right below here. It's just take the first term and then over 1 minus 1/4. And that's it. So let's find the answer here. And I get 12 divided by 3/4. If you want to grab a calculator on that, you are more than welcome to, of course. But 12 divided by 3/4 is really 12 times 4/3. And I'm getting 16. And that's it. So you can kind of see these values already fairly close to 16 just after 4 terms. But the types of numbers that are going to be added onto it are just going to get infinitely closer to 0, and so are not going to really affect the sum very much. And as a result, we're going to get the sums to get infinitely close to 16. Neat. So we're going to do a couple just repeated decimals, sort of show this, and well, let's see how it works. So example 4, everyone, if you're ready, use the fact that 0.45 repeating is really this, 45 1/100ths plus 45 10,000ths plus 45 1/1,000,000. So if you're not sure why that is, let me just come off to the side. So just kind of, that's what this is right here. And a repeated decimal, as we will see, really can be represented as an infinite geometric series. So you see that here's the 45 1/100ths right here. Let me circle that for you. And then I would add this part to it. This would be like 0.0045. So this would be 45 10,000ths. Then add this into it. This would be 45 millionths, etc., 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 infinitely. Now here's the idea. This goes, really should be a ... here, by the way. I'm going to throw that in. Basically, this is infinite. It is a series as we're adding these values together. I guess the question is, of course, is it geometric? And what we should do probably is take each of these and divide by the previous. So I'm going to do one just to kind of see and sort of extrapolate from there. But basically, I'm going to find that common ratio, everyone. So I'm going to do 45 divided by 10,000 and take that and divide it by 45 over 100. And so if I do that in each case here, I end up getting 0.01 or 1/100th. And by the way, just to get this moving along, if I did this divided by that, I also get 1/100th. Okay, so let's go for it. This is now an infinite geometric series. So what I'm going to do is add an infinite number of terms together, and it looks like it's 45 1/100ths. And then our r value is 1 over 100, that 0.01 raised to the k minus 1. And so how does this work? Well, very simply, all I need to do is take the first term and divide it by 1 minus r. And that's it. Let's clean that up a little bit here, but sorry for being redundant. Infinite geometric series. And so now, everybody, let's see what we end up getting here. I got 45 over 100, and 1 minus 1/100th should be 99 over 100, right? And by the way, if I kind of clean this up just very quickly, it looks like that goes away. And so our answer is actually 45/99, which looks really nice. I guess it can be broken down a little further, just kind of looking at that piece. This is a good answer. It does say, right, 0.45 repeating as a fraction. That is a fraction. I would argue we can probably go a little further on that, as that does reduce. So 45/99 is a good answer. I would say a better answer is probably 5/11 from what I'm seeing. So 9 goes into this and this, so 5 over 11. And let's see. Let's take a peek here. So there's only one way to kind of verify this. Let's take 5 and divide it by 11, and look what you end up getting. Perfect. So you could see that as a repeating decimal there, 0.45 repeating can be proven to be as 5 over 11. That is its value. And we did that with an infinite geometric series. All right. Now, certainly would love to blow your mind here a little bit. So example 5. First, show that 0.3 repeating is 1/3. Okay, well, we all know. I'm going to do it right up here. Let's go the other way. There's 1/3, 0.3 repeating. But let's sort of go reverse there. Let's show that 0.3 repeating really is 1/3. And then we'll take a look at that second piece. Goodness. All right, are you ready? So 0.3 repeating would be 0.333, et cetera, right? Which means 0.3 repeating is really 3/10 plus, and then another 3 right there in the hundredths, plus 3/100ths, plus, the next one is in the thousandths, so plus 3/1000ths, plus, and then dot, 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 right? It goes on infinitely. So that is an infinite geometric series. And if it's an infinite geometric series, we would find R. And again, just to kind of get this moving along a touch for us, if I take this and divide it by that, I end up getting 1/10, 0.1. This divided by that, I end up getting 0.1, 1/10. And so our R value, everybody, is going to be 1/10. And so now I'm going to treat this as an infinite geometric series where my first term is 3/10. My R value is going to be 1/10. And I have a nice, easy formula that allows us to play this out. So that's what I'm looking for right there. And let's go for it. 3/10. Down on the bottom, everybody, is 1 minus R. So 1 minus 1/10. And let's clean this up a little bit. I get 3/10 on top. Well, 1 minus 1/10 should be 9/10 there. Hoping you see that. 10s will cancel. And you end up getting 3/9, which of course is 1/3. Absolutely great. So, just using exactly what we did on example 4, I did an infinite geometric series on 0.3 repeating and have proven that it's 1/3. Now we come over to this, and this is numerically fascinating. So 0.3 repeating is 1 over 3. 0.6 repeating, by the way, is 2 over 3. And 0.9 repeating is actually 3 over 3, or actually just the number 1. So we're going to show that this value, 0.9 repeating, really is the number 1. Well, let's go for it. So it works in the same way. 9/10 plus 9/100th plus 9/1000th plus dot, dot, dot. And so what I'm going to do is add an infinite number of terms together that are geometric in nature. The R value does fit in our interval. The R value is 1/10 again. And so I have my first term, and then 1/10 raised to the k minus 1. And it's a series, so I'm adding them all together. And so what this basically says is 9/10 over 1 minus 1/10. Everyone okay with that? So just applying our nice, easy formula. A sub 1 over 1 minus r. And as you can potentially see here, I get that over that, and anything divided by itself is 1. So instead of saying I am holding 1 pencil in my hand, you can say I am holding 0.9 repeating pencil in my hand. And it means the exact same thing. Try to wrap your mind around that one. Pretty crazy, huh? So 0.9 repeating is the number 1. Cool. Hey, there's another quick proof to this, if you don't mind. If this didn't convince you that that mathematically is true, drop your pencil for just a sec, and I've got one other proof that kind of shows that that is the case. I'm going to try to find a little room for it. Here we go. I can do it right under the example 5 part. So as I said, just peek up here. If you're not convinced, I still have one more piece of the puzzle for you. So here's what I would say. Let's start out with that 0.9 repeating, everyone. So I'm going to let x equal 0.9 repeating. And what I'm going to do is manipulate this equation. And I'm going to manipulate it first, everybody, by multiplying it by 10. So everyone, multiply the left side by 10 in your mind. Multiply the right side by 10 in your mind. Again, it's okay. As long as I do the same thing to both sides, it's all good. And this would just move the decimal 1 to the right, by the way, so you'd get 9.9 repeating. Okay, sounds good. Now what I'm going to do is subtract sort of the same thing on both sides. On the left side, everybody, I'm going to subtract the x. And on the right-hand side, because x is equal to 0.9 repeating, I'm going to subtract it. So let's see if I can fit that in there, by the way. There we go. This and this I defined as the same. So subtracting it from the left and subtracting it from the right, identical. All right, let's clean it. 10x minus 1x is 9x. This, everybody, minus this takes away that part, and you end up getting 9. And take a look, everyone. So I said x was equal to 0.9 repeating, and just by manipulating that, all good math all the way through, I also proved that x is 1. So by the transitive property, this is equal to this. Pretty neat. Alrighty, let's move on. Last one. So example 6, a pendulum initially swings through an arc of 18 inches. On each successive swing, the arc is 0.98 of its previous length. So, and by the way, of means multiply. Let's just be very clear about that piece. So basically, to get any length in a particular, or any arc length, I will multiply the previous one by 0.98. I'm hoping everyone is okay with that. So whatever the first one is, you multiply it by 0.98 to get the next one. And then multiply it by 0.98 to get the next one, and the next one, and the next one. Repeated multiplication. And since we're not talking about a continuous situation, we're talking about one swing to the next swing to the next swing, we would call this geometric in nature. All right, well, let's go for it. Letter A. What is the length of the arc on the 10th swing? So one of the things you're going to have to do as you look at these problems is really interpret what the question is asking. Is it a sequence? Is it a series? Is it arithmetic? Is it geometric? Is it finite? Is it infinite? Those are definitely the things you're going to have to answer. In this case, it says, what is the length of the arc on just the 10th swing? Well, it seems to me we're starting with 18. That's the length of the arc on the first swing. 0.98 times that would be the length of the arc on the second. 0.98 times that would be the length of the arc on the third. And so when I get to the 10th, to me it just seems like the 10th value in a geometric sequence. So I'm seeing this as a geometric sequence problem. And so I'm looking for the value of the 10th term. I hope that makes sense. So the 10th result, so to speak, or the 10th value. And so as a result here, I'm just going to go a sub 10. We start with 18. And just now it's just a matter of knowing our formulas. We already said this is geometric. So I take my 18 and I multiply it by 0.98. What do I raise it to, everybody, though? The ninth. All right, I'll bring my calculator up. I'll do these all with you, I think. And so let's see, 18, times 0.98 and raised to the 9th. And so we get just over 15 inches in this case. I'll go ahead and do 15.007 inches. All right, great. So again, it's a sequence. In this case, I'm just looking for a particular value in the pattern of numbers. Letter B. I like this one. On which swing will the length of the arc be less than 12 inches? Fascinating. So it seems like we're still in a sequence here. We're looking for in this case, we have the value. We're looking for how many terms into this pattern, into this sequence, it'll hit 12. So I'm looking for n when a sub n is equal to 12. So it's still the length of the arc here. So we're looking for that value. And so I'm seeing this, everyone. Hoping you agree with that equation right there. So how many swings? So n is the number of swings. And let's see. Yeah, this looks good. So let's go ahead and divide by 18, and it looks like we'll get 2/3 on that. So 0.98 raised to the n minus 1. Now we haven't seen this in a little while, but we're getting close to the end of the semester here, and should be able to come up with something like this. How do we solve an equation where the variable is stuck in the exponent? Well, I like doing the rollover, everyone, so we haven't seen this in some time, but I would roll that 0.98 over to the other side. I'm going to have to come up here, and I would get a logarithm as a result. So log base 0.98 of 2/3 equals n minus 1. Oh, wow, that's awesome. So let's go ahead and bring the calculator up here and go ahead and get that logarithm. So for me, on my calculator, I'm going to have to do the log of 2/3 and then divide by log 0.98. Get that right there. Don't forget to add the 1, by the way, because our formula has that n minus 1 in there. So I add 1, and I get about 21.06 swings. That's when it would hit 12. So what that means, and let's go ahead and put that in just for right now. So what that means, I think, for us is on the 21st swing, it looks like it'll be a little over 12. And so on the 22nd swing, I think that's going to be our answer, is when it would hit below 12. Good, because again, this is what's called a discrete function, where we're going from one swing to the next to the next. So that number really doesn't make any sense. So we would just round up there. All right, nice. Letter C, after 15 swings, what is the total distance covered? So total distance means we're adding all the distances together. Total is sum. And so because we're talking about 15 swings, this would be a finite geometric series. Okay, perfect. So 15, and so now we go ahead and run that formula from before. I have 18, and then 1 minus 0.98 raised to the 15th over 1 minus 0.98. So again, total distance covered, adding up the first and the second and the third and the fourth and the fifth, adding them all together. And again, it's a geometric pattern here. So finite geometric series. I'll go ahead and get my calculator to do exactly this. As said, you can kind of type it in differently if you'd like. But I do 1 minus 0.98 raised to the 15th, and then divide that by 1 minus 0.98. Get that, and then don't forget multiply by that a sub 1, which was 18, and we get it just over 235 inches there. So I'll write that in. It looks like 235.29 inches. Okay, good. So a nice problem. It's putting everything together. So in this case, A and B dealt with a geometric sequence problem. C dealt with a finite geometric series. And let's look at letter D. When the pendulum comes to rest, what is the total distance covered? Now this is sort of interesting because I guess you can argue if it's always going to be 0.98 of the previous one, will it ever officially come to perfect rest? Well, no, but is it going to get infinitely close to the rest position? Yeah. And so in this case, I think we're going to add up an infinite number of values together, essentially seeing what happens as n approaches infinity. So it looks like this is going to be the case. Starting at 18, each successive swing is 0.98 of the previous one, and I'm going to do that for an infinite number of swings. It's just going to keep going and going and going, getting infinitely close to the rest position. And so what would be the total distance covered, meaning I would add all those values together? Well, let's take a look. So this one's nice and straightforward. I just do 18, 1 minus 0.98. And if you don't mind, just one quick explanation on that piece, and this is the idea right up here. It's this part that produces this part. When you take 0.98 and you raise it to larger and larger and larger values, and you can do that on your calculator if you'd like, this is going to get closer and closer and closer to 0. If this gets closer to 0, then the top gets closer to 1. And 18 times 1 is just the 18, and that's where this comes from. So let's see, I think I might be able to pull this off. 18 times 0.02, I'm getting this as 900. Might want to confirm that for me, but I'm going to run with it. Okay, that looks great. So as n gets closer to infinity, the sum gets closer to 900. All right, obviously a lot to kind of cope with here, conceptually speaking, but pretty fascinating stuff. Thank you for listening, of course.